oh, sorry, I clicked too early. Yeah, that identification model that is capable of automatically identifying the classes represented in the model, and those are representative again for this area. The red dots here are the stations that are at the moment included in the model, so used to train the model. Then here, so now we're going to go to the actual, well, preliminary results. So what do we get from the imaging system are obviously images, and here's one nice one shown here. So most important is this really good image quality that Loki gives us is a major improvement over other systems, and this great imaging quality makes it possible for us to also make very detailed models, since we are, for example, here able to distinguish just by looking at the images the species and stages down, really, yeah, with a very a lot of taxonomic detail. Here's some other diversity. So here the Calanus hyperboreus with where you can actually see inside the fat storage that Jordan was also talking about. Then here euphosit, a polycat, green worm. Then here we have also the polycat larvae, for example, or a barnacle larvae here, just to see you some of the show you some of the things we can image. So now the actual automatic identification model, it's important to know that we have 125 different classes, subclasses, and orientations in that model. Yeah, the important thing is that we have a lot of different orientations in this model that has not been done that much before. So for example, here on the right-hand side, we have this figure with the different Calanus glacialis females. So this is all the same species and the same stage. However, depending on the orientation in front of the camera, those can look really different, and that's why we subdivided here into classes, for example, the lateral view, the dorsal short view, or the dorsal long view, for example. And if we speak about an automatic identification algorithm, then we have to train that algorithm, and we did that on 12,820 manual classifications. So for 12,820 images, we told the algorithm that, well, this image is a certain taxon, so please learn the relationship. And how this relationship learning works, I'm going to talk about now. So the question is, what do we actually do with the images? Because if we look at that image, well, we can't do real science just by looking at the images. So what we do, we have to translate those images into actual values, and we do that. Well, I started calling that the zooplankton thumbprint. So what is happening is that we import all our images into this Loki browser software, where then the outline of the plankton is measured, and we extract from those images. As you can see here on the right-hand side, for example, this is the contour, the outline, and we extract 24 different parameters. So, for example, the length, the area, circularity, but also some more sophisticated things like Hu moments and Fourier descriptors. But this set of 24 parameters, that is what I call the thumbprint for each different image. So if we go then on, now that's when the actual model building happens. So we use this machine learning technique based on random forests, where those 12,820 manual identifications, so where the thumbprint is linked to what taxon it is, that goes into that random forest algorithm, and that's where it learns the relationship between this thumbprint, so the different parameters, and the taxon. And important to know is that this technique is an ensemble model technique of randomly generated decision trees. If anybody wants to know more on that, I have some extra slides that I can show after the presentation. So now we go into results. I have some results here on the model validation, and then a little insight into some ecology. So I have 3 different model validation steps. The first step is model internal validation. So when the random forest algorithm is running, it withholds 30% of the data for testing, and that is happening here. So what we see is 114 images of Calanus hyperboreus females were part of those 30%, so they were tested internally, and in 91%, for example, in this case, the algorithm classified those correctly as Calanus hyperboreus females, and so on. So then we have the smaller, younger stage 3 here. There's a smaller sample size because at the time of the year, most of the Calanus hyperboreus were already grown to be older stages, like for example here the stage 4 and 5. But we can see that the percent correct, the prediction success is relatively high, And if we look at all the 125 classes, then we have a prediction success of about 82%. And that is relatively high for that kind of modeling challenge. If we go on, a second validation step is the visual comparison of the underlying images with the automatic identification. So if we look at what does the algorithm tell us what an image is, and then I can go back to the underlying image and actually verify that with my own eyes. And if I do that verification over the 125 classes, then we get a slightly higher prediction success of 88%. And now to the last validation, which is the ground truthing, because in comparison to other systems, again, it's relatively easy with Loki to actually collect the biological sample that was imaged, to collect that afterwards, and then really compare what images did we get and what automatic identification did we get from that, and then what was really in the biological sample, and we analyze that sample then in the traditional way under the microscope. So here we see in green the biological sample analysis done under the microscope with 3 replicates here. That's where we got the error bars, and in red the results of the automatic identification. And we can see here that the results line up really nicely, and especially here for this big calanoscopod hyperboreus, and that's a really nice result. Important to know is here that we have no calanos hyperboreus stage 1 and 2, and that is, again, as I pointed out earlier, so that was a relatively, the station was relatively south in that study area, so there were none of those young stages around anymore, and that was also predicted correctly by the algorithm, which is a nice result. Now, actually, my last slide already, except for the discussion, and probably also the most interesting and important. So here we see now, if we take the automatic identified data and we plot it over the vertical water column, then we can see here, for example, well, I singled out Calanus glacialis stage 3 and 5 here because we see some very nice signals. So we have relatively big patch of those younger Calanus glacialis stage 3, which are closer to the surface, and we have also a larger patch of Calanus glacialis stage 5 closer down to the bottom, which are 2 very nice findings so far here. And if we look at the underlying fluorescence data, which was again collected at the same time also in situ, then this Calanus glacialis stage 3 patch lines very nicely up with the fluorescence peak. And what